Hello, I'm Shafayat from Professor Md Shafayat's lab at Princeton University. Today I'm going to talk about Bloch ferromagnetism of composite fermions, and the theoretical calculations of this work has been done by our collaborator at Penn State University. So what is Bloch ferromagnetism? Bloch ferromagnetism is the simplest form of itinerant ferromagnetism, where if you take a paramagnetic system at high densities and start lowering its density, so the system will become more and more interacting, and when the exchange energies will surpass the kinetic energy or the Fermi energy of the system, it will spontaneously magnetize. So you'll have a Bloch ferromagnet. The theory was given by Felix Bloch nearly a century ago. So how do we observe this? So to quantify the requirement for the Bloch ferromagnetism, we use a parameter called Rs, which is the ratio of Coulomb energy to the kinetic energy. So it denotes the interaction present in the system, and it goes as 1 over square root of n. So of course, when you lower the electron density, Rs goes up and the system becomes more and more interacting. So to observe the Bloch ferromagnetism, you need an Rs exceeding 25, which is very large. And perhaps that's why there has been no unambiguous experiment for the Bloch ferromagnetism of electrons, because it requires very low electron density to achieve such a large Rs. So we ask a question, can we observe this Bloch ferromagnetism in other fermionic system? So I'll show you our data showing that yes, we can, and we don't observe it in electrons, but we observe in another system of composite fermions. So what is composite fermions? Composite fermion is a quasi-particle that forms in the half-filled lowest Landau level of a two-dimensional electron system. So one electron couples with two flux quanta, and then it forms a bound state called composite fermions. And these composite fermions occupy a Fermi C near filling factor 1/2, just like what happens for electrons at zero magnetic field. And importantly, they have a spin degree of freedom of their own, even though they form at a finite magnetic field, which is required to reach the half-filled Landau level. So we can actually measure the spin of the composite fermion in a very straightforward way. Our platform is a gallium arsenide quantum well system, which has very high quality of mobilities exceeding 10 million centimeters square per volt second. And then we take our sample and we lithographically pattern one-dimensional superlattice on the surface, which creates a gentle density perturbation in the two-dimensional electron system. Now, when these composite fermions experience an effective magnetic field and they perform the cyclotron motion, when the diameter of this cyclotron motion becomes commensurate with the period of this superlattice, they perform a geometric resonance. And this geometric resonance is manifested as resistance minimum flanking filling factor 1/2. And we see it in the magnetotransport measurements. And just by knowing the location of this geometric resonance minima position, we can actually extract the Fermi wave vector of the composite fermion in a very straightforward way. And so what we know about the composite fermion Fermi C is the Fermi wave vector. If the composite fermions are fully polarized, they'll have only one Fermi C of one single spin, and they'll have a full polarization, P equals to 1. But when the composite fermions are only partially polarized, they will occupy two Fermi Cs of two opposite spins. And just by knowing their respective Fermi wave vector, we can deduce the spin polarization in a straightforward manner. Now, if we look at our data of these geometric resonance measurements, if we start from density 10.16 times 10 to the power 10 per square centimeter and start lowering its density down to 4.22, we see the location of the geometric resonance minima line up exactly with these vertical markings, which denote the full expected position of this geometric resonance for fully spin polarized composite fermion, Fermi C. So it's clear that down to 4.22, the locations agree very well with what's expected from a fully polarized composite fermion Fermi C. So they have only one Fermi wave vector. Now, if we go to lower densities, if you notice for starting from 4.02, the location of the geometric resonance minima start to deviate. And at some density ranges, we even see two resonance minima on one side of filling factor 1/2. So it signals that there are two Fermi wave vectors of composite fermions of two separate spin species. Now, intriguingly, when we go to even lower densities, things become simple again, and the location of these geometric resonance minima match quite well with what's expected from fully spin polarized Fermi C as we go lower and lower in densities. So we again observe only one Fermi wave vector of the composite fermions. So now we summarize our data. These black data points denote the density of the upspin composite fermion normalized by the total density, and the red data points denote the density of the downspin composite fermion, again normalized to the total density. So at high densities, the composite fermions are fully polarized, and at an intermediate density, they lose their full polarization, and strikingly, they go back being fully polarized after another density, NC1. So how do we understand the data? At high densities, composite fermions are just trivial ferromagnet. If you remember, the composite fermion have their own spin degree of freedom, and that spin polarization of the composite fermion depends on alpha, which is the ratio of Zeeman energy to Coulomb energy, and it goes as square root of n. And when the alpha becomes greater than 0.01, composite fermions become fully spin polarized. It's consistent with previous observations. And then as we go to lower in densities, this alpha becomes smaller than 0.01. So the composite fermions lose their full polarization. This is also consistent with what has been observed before. Surprisingly, again, the composite fermions become fully polarized at even lower densities. So if you think of alpha, at lower density, it's even smaller than before. So the composite fermions should lose their spin polarization gradually. However, another parameter called kappa, which is the Landau level mixing, becomes large at low densities, which is very important in this case. So kappa is just the ratio of Coulomb energy to the cyclotron energy, and it goes as 1 over square root of n. So lower the density, larger the kappa. And the theoretical calculation from our collaborators at Penn State suggests that when you have large kappa in the system, which happens in this case for low densities, the energy of the fully polarized state, the red curve, goes down faster at lower densities with respect to the energy of the spin singlet state. Now, to remind you that since composite fermions form at a finite magnetic field, so at high densities, large magnetic fields, they're fully polarized. And again, when you go to lower densities, they lose their full polarization, and now they're partially polarized. However, because of this effect of Landau level mixing or kappa, so that the energy of the fully polarized state decays faster than the energy of the spin singlet, this curve turns around, and again below another critical density, composite fermions start become fully magnetized again. And yeah, it shows a Bloch ferromagnet of composite fermions. So in summary, we observe the Bloch ferromagnetism, but not in a system of electrons, but in a system of composite fermions. And with that, I would like to conclude my talk. Thank you all for listening.